The Goblin Dwarf Planet is a name that seems to evoke images of mischief and mystery, yet this frozen world holds an allure rooted deeply in the enigmatic reaches of our solar system. Officially designated as 2015 TG387, the Goblin's orbit takes it on a path so far from the Sun that one complete journey lasts a staggering 40,000 years. Discovered in the twilight of our advancements in astronomical observation, it resides in the icy expanses beyond Pluto, within the scattered disk of the solar system, a region filled with small, icy bodies that hint at secrets yet untold. Its orbit is unlike anything we typically associate with planets. Elongated to a degree that defies simple understanding, it ventures as close as 65 astronomical units to the Sun before wandering out to distances of nearly 2,300 astronomical units. To grasp this scale, consider that one astronomical unit represents the distance from Earth to the Sun, approximately 93 million miles. This immense distance places the Goblin well beyond the Kuiper Belt, into a realm where sunlight becomes a faint whisper and temperatures plummet to extremes that challenge our imagination. The Goblin was first spotted during a survey for distant solar system objects, using the Subaru telescope located on Mauna Kea in Hawaii. Its faint, slow movement against the backdrop of stars revealed its distant trajectory. Scientists, intrigued by its orbit, recognized it as a clue, perhaps even a key, to the possible existence of a far larger entity lurking in the dark, a theoretical ninth planet, often referred to as Planet 9. The gravitational effects on objects like the Goblin suggest that such a massive body could be influencing their orbits, keeping them in an alignment that defies randomness. If Planet 9 exists, it would dwarf Earth, potentially weighing in at 10 times its mass and orbiting at distances 20 times farther from the Sun than Neptune. The Goblin's discovery adds to a growing family of distant objects whose peculiar orbits point to this hidden planetary giant. Unlike planets within the inner solar system, which were formed and influenced by the Sun's strong gravitational pull, the Goblin's distant orbit indicates an origin shaped by forces beyond what we can easily observe. Some theorize that the Goblin, along with other extreme trans-Neptunian objects, may have been gravitationally nudged into its position by close encounters with other stars during the solar system's infancy, a period when the Sun was part of a dense stellar nursery. Others propose that Planet 9, if real, continues to exert a subtle but significant influence, sculpting the orbits of these distant bodies. This tiny world, less than 200 miles in diameter, is likely a relic of the solar system's primordial days. Its frozen surface, untouched by the geological processes that constantly reshape larger planets, offers a glimpse into the conditions of our cosmic neighborhood billions of years ago. Locked in the cold embrace of the Sun's distant reach, the Goblin might be a time capsule, preserving evidence of the materials and processes that once dominated the outer solar system. These frozen remnants, scattered like breadcrumbs, could help us piece together the story of planetary formation and migration. But the Goblin's importance goes beyond its immediate physical characteristics. Its discovery has reignited curiosity about the solar system's boundaries and the interplay of forces that govern its dynamics. It challenges us to rethink the edges of our cosmic map, to question what lies beyond the faint flicker of Pluto's distant orbit. Could there be more worlds waiting to be discovered, hidden in the vast expanse of darkness that surrounds us? The Goblin reminds us of how much we have yet to learn, how the cosmos continues to surprise us, even as our instruments grow more sophisticated and our theories more refined. And yet, there is something poetic about the Goblin's slow journey. Each step of its orbit spans centuries, each return to its closest point to the Sun, witnessed only by civilizations separated by millennia. It drifts through a space so remote that it seems almost disconnected from the bustling activity of planets closer to the Sun. In its icy solitude, it carries the weight of the unknown, a silent sentinel marking the frontier of human knowledge. As we continue to search for Planet 9 and uncover more objects like the Goblin, we are reminded that the solar system is not static. It is a dynamic, evolving system filled with surprises, waiting for the patient observer to uncover. The Goblin's elongated orbit, its cold isolation, and the mysteries it hints at all serve as a reminder of the vastness and complexity of the universe we inhabit. Its discovery is not just a testament to human ingenuity, but a call to keep exploring, to keep asking questions, and to embrace the unknown. In the faint, icy glow of a world far removed from our own, we find not just a mystery to solve, but a reflection of our enduring quest to understand the cosmos. SIMP J01365663 is a name that lacks the flair of a traditional celestial wonder. Yet this object is among the most peculiar and baffling discoveries of our time. Found about 20 light-years away from Earth, it defies straightforward classification. Is it a planet? Is it a star? The answer lies somewhere in between, challenging the very framework we use to define the objects that populate the cosmos. This enigmatic entity belongs to a category known as brown dwarfs, objects too massive to be planets, but not massive enough to sustain nuclear fusion, the process that powers stars. Discovered in 2018, SIMP J01365663 immediately stood out due to its extraordinary magnetic field, a feature that exceeds expectations for an object of its type. Its magnetic strength is estimated to be 200 times that of Jupiter, the giant of our own solar system, making it an anomaly even among brown dwarfs. This magnetic field generates auroras, similar to the northern and southern lights on Earth, that dazzle across its atmosphere despite the absence of a host star to supply the charged particles typically needed to produce such phenomena. The auroras remain a puzzle, suggesting the presence of mechanisms not yet fully understood by scientists. What makes SIMP J01365663 particularly intriguing is its mass and temperature. At roughly 13 times the mass of Jupiter, it hovers at the threshold where planets end and brown dwarfs begin. Its temperature is far cooler than that of most stars, with a surface temperature similar to that of molten lava. These characteristics place it in a liminal space, blurring the boundaries between what we consider a planet and what we classify as a failed star. Its discovery has forced astronomers to revisit and refine the definitions of these celestial categories. The object belongs to a subgroup of brown dwarfs known as rogue planets or free-floating planets, drifting alone in space without a parent star. This raises questions about its origin. Was SIMP J01365663 ejected from a young star system during its formation, cast out by the gravitational interplay of other bodies? Or did it form independently, collapsing from a cloud of gas and dust too small to ignite nuclear fusion? The answers to these questions hold implications not just for this single object, but for our understanding of planetary and stellar formation. As a whole, SIMP J01365663 also offers a glimpse into the extreme diversity of objects that exist beyond our solar system. In a universe where categories often seem neatly defined, planets orbit stars, and stars shine with the energy of nuclear fusion, this hybrid reminds us that the cosmos is far more nuanced and complex. It challenges us to look beyond traditional classifications and consider that the universe does not conform to human-made definitions. Instead, it exists on a spectrum, with objects like SIMP J01365663 occupying the grey areas that spark curiosity and wonder. The discovery of such objects has been made possible by advancements in radio astronomy. SIMP J01365663 was first identified through its powerful radio emissions, a method that could revolutionize how we search for similar entities in the future. Unlike traditional methods that rely on the detection of light, radio astronomy allows us to peer into the darker corners of space, uncovering hidden treasures that might otherwise go unnoticed. This technological leap opens the door to a broader understanding of the universe, revealing objects that challenge and expand our existing frameworks. Beyond its scientific significance, SIMP J01365663 stirs the imagination. Its existence conjures images of a lone wanderer in the cosmic void, unbound by the gravitational ties that define the lives of most celestial bodies. It drifts through the darkness, its magnetic field crackling with energy, its auroras painting its atmosphere with ethereal light. It is both isolated and extraordinary, a testament to the diversity of worlds that exist in the vastness of space. The implications of this discovery extend into the philosophical realm as well. What does it mean for an object to defy categorization? In the human quest to understand the universe, we often seek to impose order and structure, creating labels and classifications to make sense of the infinite. Yet, objects like SIMP J01365663 remind us that the universe is not obligated to fit within the confines of our understanding. Instead, it invites us to embrace complexity and to find beauty in the anomalies that challenge our perceptions. SIMP J01365663 is more than a scientific curiosity. It is a symbol of the unknown. It represents the limits of our knowledge and the boundless potential for discovery. As we continue to explore the universe, searching for objects that defy explanation, we are reminded of the value of curiosity and the importance of questioning what we think we know. In the cold, dark reaches of space, this hybrid world stands as a beacon of mystery, a reminder that the cosmos is vast, strange, and endlessly fascinating. The discovery of Gaia Enceladus revealed an astonishing truth hidden within our very own galaxy. The Milky Way is not a single unified entity, but a tapestry woven from the remnants of ancient collisions. Among these remnants is an entire galaxy, Gaia Enceladus, that collided with the Milky Way billions of years ago, leaving its stars and debris embedded within our cosmic home. This revelation, uncovered by the Gaia Space Observatory, challenges how we understand the structure and history of the galaxy we call home. Gaia Enceladus came to light through an analysis of the motions, compositions, and ages of stars in the Milky Way. While most stars in the galaxy follow predictable orbits along its spiral arms, the stars from Gaia Enceladus exhibit unusual trajectories. They appear to move in chaotic, elongated paths that contrast sharply with the more orderly motions of native stars. By mapping these patterns, scientists piece together evidence of a colossal ancient collision, a galactic merger so violent that it reshaped the Milky Way's structure and added vast numbers of stars to its stellar population. This collision likely occurred around 10 billion years ago, during the Milky Way's formative years. At the time, the Milky Way was much smaller than it is today, and the collision with Gaia Enceladus acted as a kind of cosmic infusion, doubling the mass of the galaxy's stellar halo, a diffuse cloud of stars that surrounds the galaxy. The remnants of Gaia Enceladus, which include roughly 33,000 stars identified so far, now form a distinct population within the Milky Way, their unique chemical compositions and motions serving as a fingerprint of their origin. The merger was not a peaceful integration. Simulations suggest that the collision would have sent shockwaves rippling through the young Milky Way, disturbing its disk and triggering intense periods of star formation. Entire clusters of stars likely sprang into existence as the gas and dust of the two galaxies mixed and compressed. At the same time, countless stars were scattered into the outer halo, flung to the galaxy's edges by the gravitational upheaval. The evidence of this chaos remains imprinted in the orbits of the Gaia Enceladus stars, as well as in the scars etched into the Milky Way's structure. The legacy of Gaia Enceladus extends beyond its contribution to the Milky Way's stellar population. Its collision also influenced the galaxy's dynamics and evolution. For instance, the merger may have played a role in thickening the Milky Way's disk, creating the distinct division between the thin disk, where stars like the Sun reside, and the thick disk, which hosts older, more metal-poor stars. This structural layering is a defining feature of the Milky Way, and the Gaia Enceladus event provides a critical piece of the puzzle in understanding how it came to be. But Gaia Enceladus is more than just an astronomical curiosity. It is a window into the life cycle of galaxies. Galactic mergers are a fundamental aspect of cosmic evolution, shaping galaxies both large and small. They are the reason the universe's largest structures appear as they do today. Observing and understanding these events helps astronomers reconstruct the histories of galaxies, unraveling the stories of how they grew and interacted over billions of years. Gaia Enceladus serves as a local example of a phenomenon that occurs on a cosmic scale. The discovery of Gaia Enceladus also underscores the power of modern astronomy. The Gaia Observatory, launched by the European Space Agency, has revolutionized our understanding of the Milky Way by mapping the positions and movements of over 1 billion stars with unprecedented precision. By combining this data with information about stars' chemical compositions and ages, astronomers can identify ancient mergers and trace the Milky Way's history in remarkable detail. Gaia Enceladus is one of the first major findings from this mission, but it will not be the last. The data holds the potential to uncover more galactic collisions, revealing the Milky Way's past as a series of transformative events. On a philosophical level, Gaia Enceladus invites reflection on the interconnectedness of the universe. The stars that once belonged to a distant galaxy now light up the night sky above Earth, their origins interwoven with those of the Sun and planets. This blending of galaxies speaks to the ever-changing nature of the cosmos, where even the largest structures are not fixed but constantly evolving. The Milky Way, as vast and enduring as it seems, is the product of countless interactions, each one contributing to the whole. Gaia Enceladus also reminds us of the vastness of time. The collision that brought its stars into the Milky Way occurred billions of years before humanity existed, yet its effects are still visible today. It is a testament to the slow, almost imperceptible processes that shape the universe over cosmic timescales, processes that dwarf the human experience and place our existence in a broader context. In the end, Gaia Enceladus is both a discovery and a story, a tale of two galaxies meeting in the vastness of space, their stars intermingling to form a new and larger whole. It is a story of destruction and creation, of chaos and order, and of the endless cycle of change that defines the universe. And as we gaze up at the Milky Way, we are reminded that we are part of this story, our lives intertwined with the stars that once belonged to another galaxy, now shining as one in the night sky. The Veil Nebula is a hauntingly beautiful remnant of a violent cosmic past. Spanning approximately 110 light-years across and located some 2,400 light-years away in the constellation Cygnus, it is the ghostly aftermath of a supernova explosion that occurred between 10,000 and 20,000 years ago. What remains of the once massive star is a sprawling tapestry of glowing filaments, a breathtaking testament to the transformative power of destruction in the universe. The Veil Nebula captivates not only for its visual splendor, but also for the profound story it tells about the life and death of stars. When the star that created the Veil Nebula reached the end of its life, it exhausted its nuclear fuel and could no longer support itself against the relentless pull of gravity. In its final moments, the core of the star collapsed, unleashing an explosion of unimaginable force. This supernova scattered the star's outer layers into space at speeds of millions of miles per hour, creating shock waves that swept through the surrounding interstellar medium. The result is the Veil Nebula, an intricate web of glowing gas and dust shaped by the interplay of shock waves and the cosmic material they encountered. The nebula's delicate filaments are not just visually striking, they are windows into the elemental processes that sustain the universe. The colors we see in images of the Veil Nebula are produced by different elements emitting light at specific wavelengths as they are energized by the shock waves. Red hues often signify hydrogen, the most abundant element in the universe, while greens and blues point to oxygen. These elements, forged in the nuclear furnaces of the now-destroyed star, are the building blocks of future generations of stars, planets, and even life. In this sense, the Veil Nebula is not just an ending, but a beginning, a cosmic recycling process that ensures the universe remains dynamic and ever-evolving. One of the most remarkable aspects of the Veil Nebula is its clarity. Unlike many other supernova remnants, which can appear as amorphous clouds, the veil's filaments are sharply defined, almost like strands of thread woven into a vast celestial tapestry. This is partly due to the relatively low density of the surrounding interstellar medium, which allows the shock waves to maintain their coherence as they propagate outward. The nebula's structure provides astronomers with a detailed laboratory for studying the physics of supernovae and the impact these explosions have on their environments. Observing the Veil Nebula also offers insights into the passage of time on a cosmic scale. Over centuries of observation, astronomers have noted the movement of its filaments as the shock waves continue to expand outward. By comparing historical records with modern images, we can watch the slow evolution of this remnant, tracing the lingering echoes of an explosion that occurred long before human civilization existed. It is a humbling reminder of the vast timescales over which the universe operates, where even the dramatic death of a star unfolds in a timeline that spans millennia. The Veil Nebula's discovery dates back to 1784, when it was first observed by British astronomer William Herschel. At the time, it appeared as little more than a faint wisp in the night sky, its true nature unknown. Over the centuries, advances in telescope technology have revealed its intricate details, transforming it from a mysterious blur into one of the most studied and admired objects in the sky. Modern telescopes, like the Hubble Space Telescope, have captured stunning high-resolution images of the nebula, revealing its structure with unprecedented clarity. These images not only deepen our understanding of the Veil Nebula, but also inspire awe and wonder, connecting us to the vast dynamic processes that shape the cosmos. The Veil Nebula's story is also a story of connections. The star that exploded to create this nebula was once part of a larger stellar community, and its destruction has likely influenced the evolution of its cosmic neighborhood. The shock waves from the supernova have compressed nearby gas clouds, potentially triggering the formation of new stars. In this way, the death of one star sows the seeds for the birth of others, a cycle that has repeated countless times throughout the universe's history. It is a poignant reminder that endings and beginnings are inextricably linked in the cosmos, each event a thread in the grand tapestry of existence. On a more personal level, the Veil Nebula invites reflection on the nature of impermanence and transformation. It reminds us that even the most cataclysmic events can lead to beauty and renewal. The elements scattered by the supernova, carbon, oxygen, nitrogen, are the same elements that make up the air we breathe, the water we drink, and the cells of our bodies. In a very real sense, we are connected to the stars, born from the ashes of ancient explosions like the one that created the Veil Nebula. As we gaze at the Veil Nebula, we are not just looking at a distant object in space. We are witnessing a story of cosmic creation and destruction, a process that has shaped the universe and everything within it. It is a reminder of our place. In the grand scheme of things, a tiny part of a vast and interconnected cosmos, and in its ethereal beauty, it offers a moment of stillness and wonder, a chance to pause and marvel at the universe's endless capacity for transformation. Haumea, one of the strangest and most fascinating objects in our solar system, challenges our understanding of what it means to be a planet. Located in the Kuiper Belt, a region of icy bodies beyond Neptune, Haumea stands out due to its extraordinary shape, rapid rotation, and unique physical features. Discovered in 2004, this distant world has captivated scientists with its bizarre characteristics, offering a glimpse into the diversity and complexity of celestial objects in the far reaches of the solar system. Unlike most planets and dwarf planets, which are roughly spherical, Haumea is elongated, resembling a spinning rugby ball. This unusual shape is a direct result of its incredibly rapid rotation. Haumea completes one full spin in just under 4 hours, one of the fastest rotational speeds observed for any large object in the solar system. This rapid rotation causes it to flatten at the poles and stretch at the equator, creating its distinctive shape. Scientists believe this high rotation rate may be the result of a violent collision in Haumea's past, which not only set it spinning, but also shaped its current form. Haumea's surface is equally intriguing. Observations reveal that it is covered in a layer of crystalline water ice, giving it a bright, reflective appearance. This ice likely formed as a result of cryovolcanism, volcanic activity involving water and other volatile substances instead of molten rock. Haumea's surface is thought to have been resurfaced relatively recently in geological terms, perhaps due to the same collision that set it spinning. This bright surface makes Haumea one of the most reflective objects in the Kuiper Belt, second only to Pluto. Adding to its uniqueness, Haumea is the first known Kuiper Belt object to possess a ring system. In 2017, astronomers discovered a thin ring encircling the dwarf planet, a feature previously thought to be exclusive to the giant planets like Saturn and Jupiter. The exact origin of this ring is still a matter of debate, but it may have formed from debris left over from the same collision that shaped Haumea. Alternatively, it could be the result of material ejected from its surface by the rapid rotation, or other processes. The presence of the ring raises questions about how common such features might be in the Kuiper Belt and beyond, challenging previous assumptions about the conditions necessary for their formation. Haumea also has two known moons, Hi'iaka and Namaka, both named after Hawaiian goddesses associated with the mythology of Haumea, the goddess of fertility and childbirth. These moons, like Haumea itself, are thought to be fragments resulting from the ancient collision that reshaped the dwarf planet. Hi'iaka, the larger of the two moons, is particularly notable for its own bright, icy surface, hinting at a shared origin with its parent body. The study of these moons provides valuable insights into the dynamics of the Haumea system and the processes that govern the Kuiper Belt. The story of Haumea is also a story of discovery and controversy. Its detection was part of an intense race among astronomers to identify new objects in the Kuiper Belt, a region that has yielded a wealth of discoveries since the late 20th century. Haumea's unusual characteristics made it a candidate for dwarf planet status, a designation it officially received in 2008. Alongside Pluto, Eris, Makemake and Ceres, Haumea is one of the 5 recognized dwarf planets in the solar system, a testament to the diversity of planetary bodies that exist beyond the traditional definition of planets. Haumea's rapid rotation and elongated shape also make it a fascinating object for studying the physics of celestial bodies. Its behavior challenges the traditional models used to understand planetary formation and evolution, requiring astronomers to refine their theories. For instance, the relationship between its rotation, shape, and internal structure provides clues about how icy bodies in the Kuiper Belt respond to extreme forces. By studying Haumea, scientists can learn more about the physical and chemical properties of similar objects, shedding light on the conditions that prevailed in the early solar system. On a broader level, Haumea serves as a reminder of how little we know about the outer solar system. The Kuiper Belt is a frontier of discovery, home to countless objects that defy easy classification. Each new finding, whether it's a dwarf, planet, a moon, or a ring system, adds another layer of complexity to our understanding of the solar system's architecture. Haumea's unique features illustrate the richness and variety of this distant region, highlighting the need for continued exploration and study. Haumea also invites us to reflect on the dynamic and interconnected nature of the solar system. Its story is one of collisions and transformations, of destruction and creation. The events that shaped Haumea billions of years ago have left a legacy that we can observe and study today, connecting us to a time when the solar system was still forming. In its icy surface, rapid rotation, and shimmering ring, Haumea carries the scars and beauty of its history, offering a glimpse into the processes that continue to shape the cosmos. As we peer into the depths of the Kuiper Belt, Haumea stands as a testament to the wonders of the unknown. It challenges our assumptions about what a planet can be, inspiring curiosity and wonder in equal measure. Through its mysteries, Haumea reminds us that the universe is far more intricate and surprising than we can imagine, and that every discovery, no matter how distant, enriches our understanding of the world we inhabit. Planetary nebulae are among the most stunning and enigmatic structures in the cosmos, marking the final chapters in the life cycles of stars similar to our Sun. Despite their name, planetary nebulae have nothing to do with planets. The term dates back to the 18th century when astronomers peering through early telescopes noted these objects' rounded, planet-like shapes. However, their true nature is far more complex and awe-inspiring. These ephemeral clouds of glowing gas and dust are the remnants of stars, a fleeting yet brilliant spectacle that offers profound insights into the processes of stellar evolution and the interconnection of life and death in the universe. The formation of a planetary nebula begins when a star like the Sun reaches the end of its life. After burning through the hydrogen fuel in its core, the star expands into a red giant, shedding its outer layers into space over tens of thousands of years. As the core of the star becomes exposed, it contracts and heats up, transforming into a dense, hot white dwarf. The intense radiation from this white dwarf energizes the ejected material, causing it to glow and form the intricate, multicolored patterns that define planetary nebula. This process represents the final visible stage of a medium-sized star's life, lasting only a few tens of thousands of years, a blink of an eye on cosmic timescales. What makes planetary nebulae so captivating is their extraordinary variety of shapes and colors. While many are roughly spherical, others display complex structures such as bipolar lobes, spiral patterns, or even shapes resembling butterflies. These diverse forms are the result of interactions between the ejected material and the star's environment, as well as the influence of magnetic fields, stellar winds, and companion stars. For example, a star with a close binary companion can produce a nebula with a highly symmetrical or axis-aligned structure, as the gravitational interplay between the two objects sculpts the material into distinctive patterns. The colors of a planetary nebula arise from the elements within the ejected material and the specific wavelengths of light they emit. Hydrogen, the most abundant element, glows red or pink, while oxygen emits a vivid green or blue. These colors are not only beautiful, but also scientifically significant, as they reveal the chemical composition of the star and its surroundings. Planetary nebulae act as cosmic forges, dispersing elements such as carbon, nitrogen, and oxygen into space, materials that will eventually form new stars, planets, and even the building blocks of life. In this sense, they are not merely endpoints, but essential contributors to the ongoing cycle of creation in the universe. Observing planetary nebulae provides astronomers with a wealth of information about stellar evolution, the chemical enrichment of galaxies, and the dynamics of interstellar space. The intricate structures and glowing shells serve as laboratories for studying the physics of gas and plasma, as well as the effects of high-energy radiation. By analyzing the light emitted by a nebula, scientists can determine its temperature, density, and composition, piecing together the history of the star that created it. These studies also help refine our understanding of how stars evolve and die, offering a glimpse into the eventual fate of our own sun. The idea that our sun will one day create a planetary nebula is both humbling and poetic. In approximately 5 billion years, the sun will exhaust its hydrogen fuel and expand into a red giant, engulfing the inner planets, including Earth. After shedding its outer layers and forming a nebula, the sun's core will shrink into a white dwarf, a faint, slowly cooling remnant of its former self. The nebula it leaves behind will glow for a brief moment in cosmic time, before fading into invisibility, its material dispersed into the galaxy to seed new stars and planets. This cycle of death and renewal is a reminder of the interconnectedness of all things in the universe, a process in which destruction paves the way for creation. The study of planetary nebulae also raises profound philosophical questions about impermanence and transformation. These objects are, in essence, the last luminous gestures of dying stars, a fleeting yet dazzling display that eventually fades into the darkness of space. Their transient nature contrasts sharply with the vastness of cosmic time, offering a poignant reminder of the ephemeral beauty of all things. Yet, in their short-lived brilliance, planetary nebulae leave an indelible mark on the universe, enriching it with the elements necessary for new beginnings. They are both an end and a promise of what is yet to come. Some of the most famous planetary nebulae, such as the Ring Nebula, the Helix Nebula, and the Cat's Eye Nebula, have become iconic symbols of the cosmos, their intricate structures, captured in breathtaking detail by telescopes like Hubble. These images, with their vivid colors and mesmerizing forms, evoke a sense of wonder and connection to the universe. They remind us that even in the vastness of space there is beauty, purpose, and a story being told, a story of transformation, resilience, and the enduring cycle of life and death. In a way, planetary nebulae are cosmic artists, painting the universe with the remnants of their existence. Each nebula is unique, shaped by the specific conditions of its formation and the star that created it. Yet, they all share a common theme: the inevitability of change and the enduring legacy of what came before. Through their fleeting brilliance, Planetary nebulae teach us that even the end of a star's life can be a moment of profound beauty and significance, a final act that leaves the universe richer and more complex than it was before. Cosmic voids are some of the most mysterious and fascinating structures in the universe. These vast regions of space are defined by their emptiness, large, nearly empty expanses between galaxy clusters where very few galaxies exist. They are often referred to as the large-scale structure of the universe, representing the gaps in the cosmic web that forms the foundation of our universe. While the term void implies emptiness, these regions are far from empty in the traditional sense. They are filled with very low-density gas, dark matter, and dark energy, components that continue to elude direct observation but shape the universe's evolution. The existence of cosmic voids challenges our understanding of the universe's structure and the forces that govern it. These vast regions can span hundreds of millions of light-years across, yet they contain remarkably few galaxies. This has led scientists to rethink the distribution of matter in the cosmos. If we imagine the universe as a vast, interconnected web of galaxies, the voids form the empty spaces between the strands, much like the gaps in a spider's web. Their presence is not random, but is instead a result of the gravitational influence of matter over time, which has caused galaxies to clump together while pushing other regions into a state of near-complete emptiness. The largest known void, the Great Void, or cosmic supervoid, stretches over 3 billion light-years across. This extraordinary emptiness is mind-boggling in its scale, dwarfing the size of typical voids and creating a vast region where the usual cosmic activity is almost entirely absent. Voids are not just empty spaces, but regions where the fabric of the universe behaves in unusual ways. For instance, light traveling through a void will experience less gravitational lensing, meaning it may travel through these areas more directly than in regions filled with galaxy clusters. This makes voids key areas for studying the distribution of matter and the behavior of light in deep space. Despite their emptiness, voids play a crucial role in the evolution of the universe. They are not entirely devoid of matter. There are still some faint galaxies and diffuse gas scattered throughout these regions. In fact, voids are essential in the process of galactic evolution. The very emptiness of these regions allows for the creation of the large-scale structures we see today. Voids also influence the motion of galaxies as they act as funnels for matter, guiding galaxies toward the denser areas of the universe, where clusters and superclusters of galaxies form. In a way, voids are part of the larger cosmic dance, subtly shaping the structure of the universe even as they appear to be nothing more than empty space. But voids are not merely vast stretches of emptiness. They are also crucial to understanding dark energy, the mysterious force driving the accelerated expansion of the universe. Dark energy, thought to make up about 70% of the universe's energy content, has an increasingly noticeable effect in regions where matter is sparse. In the relatively empty voids, dark energy can have a stronger influence, pushing the fabric of space apart more rapidly than in areas filled with galaxies. This means that the study of cosmic voids can offer important insights into the nature of dark energy and its role in the universe's expansion. The existence of voids also raises deep philosophical questions about the nature of space itself. These vast, empty regions challenge our intuitions about the universe. How can something so large be so empty? What does it mean for space to be empty when it is still filled with dark matter and dark energy, substances that we cannot directly observe but that govern the behavior of galaxies? In a way, voids embody the mysteries of the universe. Spaces that appear to be nothing but are actually brimming with unseen forces, the very fabric of reality that remains hidden from our perception. In considering voids, we are also confronted with the question of scale and perspective. On a cosmic scale, the universe is made up of vast networks of galaxies and clusters, with voids serving as the great silences between the stars. Yet even within these seemingly empty spaces, there is much to discover. By studying voids, scientists can learn more about the fundamental structure of the universe, the distribution of matter, and the nature of the forces that govern the cosmos. These studies have the potential to unlock deeper mysteries about the origins of the universe, the expansion of space, and the fate of the cosmos itself. For all their emptiness, cosmic voids remind us of the scale of the universe, both in terms of its size and its complexity. They serve as a humbling reminder that even in the most barren places in the cosmos, there are forces at work that shape the universe in ways we can only begin to understand. As we look deeper into these vast voids, we are reminded that the universe is not just a collection of galaxies and stars, but a dynamic, ever-expanding expanse that continues to surprise us with its hidden wonders. The study of voids is a journey into the heart of the unknown, where the absence of matter may be just as important as the presence of stars and galaxies. The James Webb Space Telescope, JWST, is a marvel of modern science, a symbol of human curiosity and technological achievement. Launched in December 2021, it is the most powerful space telescope ever built, designed to peer deeper into the universe than any of its predecessors. Positioned at the second Lagrange point, L2, about 1.5 million kilometers from Earth, it is far beyond the reach of atmospheric interference, allowing it to capture the most detailed images of the cosmos. What makes JWST so extraordinary is not just its ability to capture stunning visuals, but its capacity to answer some of the most profound questions about the universe's origins, its evolution, and the very nature of existence itself. One of JWST's most significant contributions is its ability to observe the oldest galaxies in the universe. These galaxies formed just a few 100 million years after the Big Bang, a time when the cosmos was still in its infancy. The telescope's infrared capabilities allow it to see through cosmic dust and observe distant objects whose light has been stretched out by the expansion of the universe, a phenomenon known as redshift. This has enabled JWST to capture the light emitted by galaxies that formed as early as 235 million years after the Big Bang. These discoveries are invaluable for understanding the formation of the first galaxies, stars, and elements in the early universe. In many ways, JWST represents the culmination of decades of astronomical research and technological development. Unlike the Hubble Space Telescope, which primarily observes in visible and ultraviolet wavelengths, JWST is optimized for infrared observation. This makes it uniquely suited for studying objects that are too faint or distant to be seen in visible light, such as the earliest galaxies, the formation of stars, and the inner workings of distant nebulae. The telescope's advanced instruments, including the near-infrared camera, NIRCam, mid-infrared instrument, MIRI, and the near-infrared spectrograph, NIRSpec, allow it to capture unprecedented detail in the infrared spectrum, revealing hidden layers of the universe that were previously beyond our reach. One of the most groundbreaking discoveries made by JWST is the identification of the oldest known galaxy, Sears 93316, located an astounding 35 billion light-years away. This galaxy formed just 235 million years after the Big Bang, making it a crucial piece of the puzzle for understanding the early stages of cosmic evolution. The light from this galaxy has traveled through the universe for over 13 billion years, and its discovery provides a glimpse into a time when the universe was still in its infancy. By studying these distant galaxies, scientists can learn about the conditions that led to the formation of the first stars and galaxies and how they contributed to the evolution of the cosmos. JWST's ability to observe distant galaxies also has profound implications for our understanding of dark matter and dark energy. These mysterious substances, which together make up about 95% of the universe's total energy content, have long eluded direct detection. However, by studying the way light from distant galaxies bends and distorts as it passes through gravitational fields, a phenomenon known as gravitational lensing, scientists can gain insights into the distribution of dark matter in the universe. Similarly, JWST's observations of galaxy clusters and supernovae can help refine our understanding of dark energy, the force that is driving the accelerated expansion of the universe. In addition to studying distant galaxies, JWST is also transforming our understanding of star formation. The telescope is able to observe the formation of stars and planetary systems within nebulae, clouds of gas and dust where new stars are born. These regions are often shrouded in dust, making them difficult to study with visible light. However, JWST's infrared capabilities allow it to peer through these dusty clouds and observe the birth of stars in incredible detail. This has already led to groundbreaking discoveries, such as the identification of protoplanetary disks, structures of gas and dust surrounding young stars that will eventually form planets. Another major achievement of JWST is its contribution to the study of exoplanets. Over the past few decades, astronomers have discovered thousands of planets orbiting stars outside our solar system, many of which are located in the habitable zones of their stars, the regions where conditions may be suitable for liquid water to exist. By studying the atmospheres of these exoplanets, JWST has the potential to detect signs of life. The telescope's ability to analyze the chemical composition of exoplanet atmospheres, including the presence of molecules like oxygen, methane, and carbon dioxide, could offer clues about the potential for life on distant worlds. This has profound implications for our search for life beyond Earth and our understanding of the conditions that make a planet habitable. The discoveries made by JWST not only expand our knowledge of the universe, but also inspire profound philosophical and existential questions. As we peer deeper into the cosmos, we are confronted with the vastness and complexity of the universe. How did it all begin? What is the true nature of dark matter and dark energy? Are we alone in the universe, or are there other forms of life waiting to be discovered? These questions are not just scientific, they are fundamental to our place in the cosmos. As we unravel the mysteries of the universe, we come to realize that our understanding of the cosmos is inextricably linked to our understanding of ourselves. The work of the James Webb Space Telescope is only beginning, and its potential is boundless. It is poised to transform our understanding of the universe and our place within it. As we look to the stars, we are reminded that our quest for knowledge is a journey that will never truly end. For with each discovery, new questions emerge, pushing us ever forward into the unknown. The answers we seek may never be fully realized, but the pursuit of those answers is what drives us to explore, to wonder and to dream. And in that pursuit, we come ever closer to understanding the profound mysteries of existence itself. Asteroids, often regarded as the leftovers from the early solar system, are fascinating relics that offer a glimpse into the formation of our solar system. These rocky or metallic bodies, some as small as pebbles and others as large as entire moons, orbit the sun and have remained largely unchanged for billions of years. Unlike planets, which have undergone significant geological and atmospheric evolution, asteroids are essentially frozen time capsules, preserving the conditions of the solar system during its formative years. Their study provides invaluable insights into the building blocks of planets and the processes that led to the creation of our own world. The role of asteroids in the formation of planets cannot be overstated. In the early solar system, dust and gas coalesced to form planetesimals, small, solid bodies that eventually grew into planets. Asteroids are essentially the remnants of these planetesimals left behind as the larger bodies formed. They are often found in the asteroid belt, a region between Mars and Jupiter, but they can also be found scattered throughout the solar system, including near-Earth asteroids that cross our planet's orbit. While the asteroid belt contains the largest concentration of these objects, asteroids are not confined to a single region of space. Some asteroids, known as Trojans, share an orbit with larger planets like Jupiter, while others, called centaurs, orbit between Jupiter and Neptune. Asteroids are made up of a variety of materials, ranging from rocky substances to metals, and even water ice in some cases. This diversity reflects the different conditions under which they formed. Some asteroids, such as carbonaceous asteroids, contain organic compounds, and scientists believe they may hold the key to understanding the origins of life on Earth. In fact, some scientists hypothesize that asteroids may have played a crucial role in delivering the necessary ingredients for life, such as water and organic molecules, to our planet in the early stages of its development. This idea is known as the panspermia hypothesis, which suggests that life, or at least the building blocks of life, may have been spread across the universe by asteroids and comets. While asteroids are often considered harmless, they can also pose a significant threat to Earth. Over the course of history, asteroid impacts have had profound effects on the planet, including the mass extinction events that wiped out the dinosaurs 66 million years ago. The possibility of a future asteroid impact has led scientists to develop strategies for detecting and potentially deflecting hazardous asteroids. The study of near-Earth asteroids is therefore not just a scientific pursuit, but also an essential part of planetary defense. Several space missions, including NASA's OSIRIS-REx and Japan's Hayabusa 2, have been launched to study and collect samples from asteroids in order to better understand their composition and potential hazards. In addition to their scientific value, asteroids are increasingly seen as potential resources for future space exploration. As humanity looks to expand beyond Earth, asteroids could serve as valuable sources of raw materials. Their proximity to Earth and the fact that they contain valuable metals such as platinum, nickel, and iron make them prime candidates for asteroid mining. This concept, known as space mining, could provide a sustainable source of resources for future space missions, particularly as we explore the Moon, Mars, and beyond. Some companies are already investigating the possibility of mining asteroids, and while the technology is still in its infancy, the idea holds great promise for the future of space exploration. Asteroids also offer a unique opportunity for exploring the early solar system's dynamics. By studying their composition and distribution, scientists can learn more about the processes that shape the solar system's architecture. For example, the presence of certain types of asteroids in specific regions of the solar system can provide clues about the migration of giant planets, such as Jupiter, and the gravitational interactions that led to the current configuration of planets and smaller bodies. Asteroids can also shed light on the formation of the solar system's chemical composition, helping scientists understand the origins of different elements and molecules that make up planets and life itself. While asteroids may seem like distant, cold objects drifting through space, their study has profound implications for understanding our place in the universe. They challenge our understanding of the origins of life, the potential for resources in space, and the delicate balance of forces that govern the solar system. In a way, asteroids represent the very beginnings of planetary formation, the building blocks of worlds, and the potential for future exploration. As we continue to study and learn from these fascinating objects, we uncover more about the history of our solar system and the possibilities that lie ahead for humanity as we venture further into the cosmos. Through the lens of asteroid exploration, we are not just looking back at the past, but also forward to the future, where the resources and knowledge we gain could one day help us reach for the stars. Planets with two suns, often portrayed in science fiction such as the iconic world of Tatooine from Star Wars, present a compelling challenge to our understanding of planetary systems and stellar formation. While these fictional worlds captured our imagination, they are not purely a creation of fiction. In reality, astronomers have discovered numerous exoplanets that orbit binary star systems, systems where two stars orbit a common center of mass. These discoveries open up fascinating possibilities regarding how planets might form, how they might sustain life, and how their climates could differ drastically from those on Earth. Binary star systems are relatively common in the universe, with estimates suggesting that about half of all stars in the Milky Way exist in pairs or multiple star systems. This makes the discovery of planets orbiting two stars even more intriguing. The dynamics of a planet in such a system are far more complex than those in our solar system, where a single star governs the motion of all the planets. In a binary system, the gravitational pull from two stars could create a wide variety of orbital configurations, depending on the distance between the two stars and the planet's position relative to them. These orbital dynamics could lead to strange and unpredictable planetary environments, with extreme seasons, fluctuating day lengths, and potentially very different climates compared to Earth. In a planet orbiting two stars, the planet might experience what's known as a circumbinary orbit, where it orbits around both stars. Depending on the orbital configuration, the planet could have a unique set of day-night cycles. If the stars are close to each other, the planet could be locked in a stable orbit that keeps it within the habitable zone, the region around the stars, where liquid water could exist. However, this would also mean that the planet experiences dual sunsets or sunrises, a breathtaking and surreal phenomenon. The gravitational forces from two stars could also impact the planet's rotation, potentially causing it to have a tilted or erratic spin, which would further complicate its climate and seasons. Some of the most fascinating discoveries regarding planets with two suns come from the Kepler Space Telescope, which has found several such planets orbiting binary star systems. One example is Kepler 16b, a planet located about 200 light-years from Earth. This planet, roughly the size of Saturn, orbits two stars, one much like our Sun and the other smaller and cooler. Kepler 16b's atmosphere, composition, and potential habitability are still being studied, but its discovery has sparked new questions about what makes a planet truly habitable. Could life exist on a world with two suns? What would it be like to live under a sky where two stars rise and set each day, casting ever-changing shadows on the ground? While binary star systems might seem like an exotic and extreme environment for life, some scientists believe that planets in these systems could indeed harbor life. The key to this is the stability of the planet's orbit. If the planet is in a stable orbit within the habitable zone of its binary stars, it might have conditions conducive to life, despite the complexities of living with two suns. The primary challenge would be the extreme fluctuations in temperature, but if a planet can maintain a stable atmosphere, it could potentially regulate temperature fluctuations and provide a habitable environment. These kinds of planetary systems could also offer unique evolutionary pressures that might result in entirely different forms of life compared to those on Earth, leading to a diversity of life forms and ecosystems previously unimaginable. The discovery of exoplanets in binary systems also raises profound questions about our own solar system's uniqueness. Until recently, the idea of planets in multiple star systems was relegated to the realm of fiction. But as technology has advanced, our ability to detect such planets has expanded. With missions like the James Webb Space Telescope and the continued study of distant exoplanets, scientists are now learning more about the variety of planetary systems in the universe and how they differ from our own. As we explore these distant worlds, we are forced to reconsider our assumptions about the possibilities for life beyond Earth and the factors that contribute to the habitability of a planet. The notion of planets with two suns also invites speculation about what it would be like to live on such a world. Imagine standing on the surface of a planet where two stars shine in the sky, casting different colors and shadows across the landscape. The effects of having two suns would not be limited to just the visual aspect. The climate, the biological rhythms of life, and even the day-night cycle would all be profoundly different. Such a world would challenge the very concept of what it means to live on a planet, forcing us to rethink the environmental factors that shape life. Would the creatures of such a world have evolved differently? How would their biological clocks be synchronized to two stars instead of one? Planets with two suns offer a glimpse into the variety of possibilities that exist in the universe. They remind us that the universe is vast and full of surprises, and that the conditions for life may not be as narrow or as Earth-centric as we once believed. As we continue to explore the cosmos and study exoplanets in binary star systems, we are bound to uncover more about the potential for life in these exotic and far-flung environments. The discovery of such planets challenges our understanding of planetary formation, life's adaptability, and the unique conditions required for a habitable world. With each new discovery, we are reminded that the universe is full of wonder and mystery waiting to be explored. The James Webb Space Telescope, launched in December 2021, has quickly become one of the most significant tools in modern astronomy. It promises to reveal unprecedented details about the universe, pushing the boundaries of what we know about space, time, and the origins of the cosmos. Among its many groundbreaking discoveries, one of the most awe-inspiring is the identification of the oldest known galaxy, Sears 93316, located an astonishing 35 billion light-years away. This galaxy formed just 235 million years after the Big Bang. Its discovery raises profound questions about the early universe, the formation of galaxies, and the potential for life in distant corners of the cosmos. The discovery of Sears 93316 is not just about the galaxy itself, but about what it represents. This galaxy is part of a broader effort to peer deeper into the universe's history than ever before. The James Webb Space Telescope, with its advanced infrared capabilities, is capable of observing light that has traveled for billions of years, allowing us to see galaxies as they were when the universe was still in its infancy. As the light from distant objects travels toward us, it undergoes a phenomenon known as redshift, where the wavelength of light stretches out, shifting it toward the red end of the spectrum. The longer the light has traveled, the more it is stretched, enabling us to look back in time and witness the formation of stars, galaxies, and other cosmic structures. Sears 93316 is a key piece of this puzzle. It is one of the most distant galaxies ever discovered, pushing the limits of our ability to observe the early universe. What makes this galaxy particularly intriguing is that it formed just a few 100 million years after the Big Bang, during a time when the universe was still undergoing significant transformations. The fact that a galaxy could form so early in the universe's history challenges existing models of galaxy formation and raises new questions about how the first stars and galaxies came to be. Was there a different set of conditions in the early universe that allowed galaxies like Sears 93316 to form so quickly, or was this galaxy simply an anomaly? One of the most profound implications of this discovery is the possibility that galaxies, like Sears 93316, could have harbored conditions suitable for life. The early universe was a much harsher and more chaotic place than the one we inhabit today. With intense radiation, frequent supernova, and massive black holes at the centers of galaxies, it would have been an incredibly hostile environment for life as we know it. However, this galaxy's early formation suggests that galaxies might have formed more rapidly than previously thought, providing a window of opportunity for the emergence of life in these early cosmic epochs. Could there have been conditions for life to arise in such a distant and ancient galaxy, even if it was short-lived? What kind of life might have existed in such an environment if it did at all? The discovery of Sears 93316 also invites us to reconsider the nature of life and its potential existence elsewhere in the universe. For decades, scientists have been searching for planets and moons that could harbor life, focusing on worlds with conditions similar to Earth. However, this new discovery suggests that life might not need to arise in a habitable zone similar to Earth's. Instead, it could emerge in vastly different environments with radically different conditions. Perhaps the chemical building blocks of life are more versatile than we have previously imagined, and life could potentially form under a broader range of circumstances. If life existed in the early universe, what might it have looked like? Would it have been microbial, or could it have developed into something more complex? Sears 93316 and other discoveries like it also remind us of the vastness of the universe. The fact that we are able to observe such distant objects is a testament to the technological advancements that have allowed us to see deeper into the cosmos than ever before. And yet, these galaxies, these stars, and these distant worlds are only a fraction of the universe we have yet to explore. As the James Webb Space Telescope continues its mission, more discoveries like Sears 93316 will undoubtedly reshape our understanding of the universe and our place within it. Each new finding brings us closer to answering the most fundamental questions about the nature of the universe, the origins of life, and the potential for life beyond Earth. In a sense, the discovery of galaxies like Sears 93316 challenges our perception of time and space. It forces us to confront the vastness of the universe and the possibility that life might exist far beyond the confines of our own planet. Just as the universe has undergone profound changes since the Big Bang, so too might our understanding of life's origins evolve as we continue to explore the far reaches of space. The search for answers to these questions is one of the most exciting frontiers of modern science, and with each new discovery, we move closer to understanding the profound mysteries of the universe. The journey of exploration is just beginning, and with the James Webb Space Telescope at the forefront, we are poised to uncover even more mind-blowing wonders in the cosmos.